In this video, we are going to go over what quantum numbers are. We are going to go over what they are, 4 types, relationships of each type, cheat hacks, and sample problems. Quantum numbers, simply put, are a way that atoms are organized. That's all you need to know as a student working through this class. While you may be told that quantum numbers have certain shapes, what you really need to know is that there are 4 types of quantum numbers. Type 1, n, is the principal quantum number. And n can have the following values. N can be 1, 2, 3, 4, and all the way over to, in theory, infinity. But in your classes, all you're ever going to use is 1, 2, 3, and 4. L is the angular quantum number. L is going to be less than or equal to n minus 1. Or you could express that as n is going to be greater than or equal to L plus 1. ML is what's called the azimuthal quantum number, or the magnetic quantum number. ML is going to be equal to a range from negative L all the way up to positive L. So if you have an L value of 2, your ML value is going to be a range of -2, -1, 0, +1, and +2. And it could be either of the 5 values unless you're told other things. Finally, MS is the magnetic spin. Magnetic spin, MS, can be either +1/2 or -1/2. In an orbital, if it is +1/2, your electron arrow will point up. And if it's -1/2, your electron arrow will point down. This is all you need to know. Now let's go over the relationships of each type to each other once more. For n to L, we can say that n is going to be greater than or equal to L plus 1. Or L is going to be less than or equal to n minus 1. For L to ML, we know that ML is going to be between -L and positive L. And finally, for n to ML, what we can say is that if L is less than or equal to n minus 1, we can say that ML is going to be minus n minus 1, then ML, up to positive n minus 1. You may not need to know this for the sake of your class, but it's worth knowing just in case. We can also put this into a Venn diagram and say that n is going to be greater than or equal to L plus 1. L is going to be less than or equal to n minus 1. Then for L and ML, we can say that minus L is going to be less than or equal to ML, which is going to be less than or equal to positive L. Last but not least, we can say how n is related to ML by saying that minus n minus 1 is less than or equal to ML, which is less than or equal to n minus 1. Now, this is a good amount of information to take in, and I still remember when I was a student learning this for the first time, it made no sense. So go ahead, take a 5-minute breather, go pee, relax your brain, smell the flowers. Welcome back. Now you're ready for the good stuff. This stuff is what your professor has been gatekeeping from you. The first cheat hack is L values. So for L values, I want you to make the following chart. For all s orbitals, L is always going to be equal to 0. For all p orbitals, L is always going to be equal to 1. For all d orbitals, L is always going to be equal to 2. And for all f orbitals, L is always going to be equal to 3. and this is always true. So put a big star by it so you know to come back to it. This is never not always true. Finally, here's your ML hack. For all ML values, start by making an energy diagram like so. We know that for n equals 1, we have only S values. For n equals 2, we have S and P values. For n equals 3, we have S, P, and D values. And for n equals 4, we have S, P, D, and F values. All S orbitals hold one slot, one orbital. All P orbitals hold 3 orbitals, px, py, and pz. All D orbitals hold 5 orbitals, 1, 2, 3, 4, 5. And all F orbitals hold 7 slots. Now, in red, I am going to label the ML values below each orbital. For S, we have 0. For P, we have 0 here. For D, we have 0 in the center, and again for F, 0 in its center. Then we have -1, +1, -2, -1, 0, +1, +2, then -3, -2, -1, 0, +1, +2, and +3. The values in red are the ML values. And also I want you to notice that the rightmost value symbolizes the L value for every orbital. For S, its rightmost L value is 0. For P, its rightmost L value is 1. For D, its rightmost L value is 2. And for F, its rightmost ML value, that equals L, is 3. Now I want to go over some sample problems with you. First and foremost, find the maximum number of electrons that share n equals 4 and ML equals +1 quantum numbers. What I want to do here is draw an energy diagram and label all the orbitals that I'm going to experience in n equals 4. Because we're in n equals 4, we're going to have 4 types of orbitals we're dealing with: S, P, D, and F. S has 1 slot, P has 3 slots, D has 5 slots, and F has 7 slots. Now to label the ML values, all center values are 0. Then all values to the left are -1. All values to the right are +1. And so on and so forth. Now we just need to fill in the electrons. I'm going to put those in blue. For maximum number of electrons, that means that every single slot is filled. Every single slot has 2 electrons, as that is what its maximum is. We're going to put our electrons in order like this so that we obey Hund's rule. Fantastic. Now we need to identify which of those electrons in the n equals 4 subshell has ML equals +1. And here we see 3 different slots that have n equals 4 and ML equals +1 quantum numbers, telling us that the maximum amount of electrons that share both of those conditions are 6 electrons. Wonderful. This problem is now telling us to find the error in the following set of quantum numbers, then make a correction to fix the error. So first and foremost, with number A, we have n equals 2. That's given, and now we just have to see how L, ML, and MS compare. For L, we know that n cannot be equal to L. N is going to be greater than or equal to L plus 1, or L is going to be less than or equal to n minus 1. Nowhere in those formulas are we told that they can be equal to each other, so for that reason, it's wrong. In order to make the formula right, we can make n any value bigger or equal to L plus 1. So if L equals 2, we can say that n can be 3, 4, or beyond. For number 2, we're given that n equals 1, and now we have to see how L, ML, and MS compare. For n equals 1, L can be 0, as L is going to be less than or equal to n minus 1. And if n equals 1, L is going to be less than or equal to 1 minus 1, telling us that L is going to be less than or equal to 0. L values start from 0, so in this case, L is just equal to 0. So that's fine. ML is a range of negative L to positive L. So if negative L is 0 and positive L is also 0, we know that ML is going to equal 0. So that's also fine. But for MS being equal to 1, that's not fine. MS can only be positive 1/2, or MS can only be negative 1/2. It can't be any other value. So for that reason, that's the error. To make the problem correct, we just need to set MS to either positive 1/2 or negative 1/2. For part C, we're being told that n equals 3, so let's see how L, ML, and MS compare. For n equals 3, L can be equal to 0, 1, or 2, as that follows the formula. So that's fine. For ML, we know that ML is going to be a range from anywhere from negative L up to positive L. So in this case, that's going to be anywhere from negative 2 up to positive 2. And because 3 is not in that range, that's where the problem is wrong. And MS is within our 2 possibilities, so we're good there. In order to make the problem correct, what we need to do is we need to change ML to be -2, -1, 0, +1, or +2. If it's any of those values, then the quantum number would be right. And finally, for problem 4, we're being told that n equals 0, but that's not true. N can only start from 1, 2, 3, or above. So with that makes the problem, in and of itself, incorrect. But to correct the problem, we need to say that n equals 2 or higher. Because if L is equal to 1, n needs to be at least one number bigger than L. So if n equals 2, L could equal 1. ML would be the range from -1 up to +1, so that works. And MS being +1/2 also works as well. In our last sample problem that we're going to go over together today, we need to assign N, L, ML, and MS configurations to the red electron in the following electron configuration. With part A, we have an orbital with 5 slots. And a 5-slotted orbital is a d orbital. All d orbitals, according to our chart that I showed you a couple pages ago, all d orbitals have an L value equal to 2. For n values, we are being told that it's on this third circle. When it comes to n values, circle 1 is n equals 1, circle 2 is n equals 2, and circle 3 is n equals 3. So n is equal to 3. For ML, we know that we can label underneath our orbitals to figure out what ML is. The centermost slot has an ML of 0, then +1, +2, -1, and -2. In this case, the red electron has an ML value of +1. Finally, this arrow is pointing down, which tells us that our MS value is MS equals -1/2. And these would be your N, L, ML, and MS configurations for part A. For part B, we have a 3-slotted orbital. That's a p orbital. All p orbitals have an L value of L equals 1. So our L value is 1. Our N value, this is your electron configuration, in p orbitals start at an n value of 2. So our n value is n equals 2, as shown here. For our nl value, we can label our chart as usual. Center is 0, right is +1, left is -1, telling us that our nl value is -1. And last but not least, our ns value is going to be +1/2 because our arrow points up. So these are going to be your quantum numbers for part A and for part B. So how do you feel at the end of the day? Do you think you need more practice? Do you still have questions? Did I miss something in my explanation? Did you have a test on this and it went great? Or even better, are you able to convince your teacher to play this video in her next class? Let me know in the comments and I'm happy to respond to all of them. Thanks for watching, have a great rest of your day, and see you in the next video.